today again I am going to discuss vibrational spectroscopy. So, in the last lecture we looked at how to calculate energy of vibrational levels and what are the selection rule. In this lecture I will just first go through recap of the last lecture and then I will discuss Raman vibrational spectroscopy and application of IR spectroscopy for various purpose in various industry and in various applications. When we solved the Schrodinger equation for vibrational or harmonic oscillator, what we got is a wave function. A wave function is given by this formula where NV is normalization factor, and then you have a Hermite polynomial and multiplied by your exponential minus alpha x square by 2. So, this is your allowed wave function for vibrational level. NV is given by this formula and then alpha is in terms of reduced mass and force constant. You can also calculate energy of various vibrational levels, and that is given by your V plus half h nu or V plus half h bar omega. So, nu is your frequency and omega is angular frequency. We also discussed in the last lecture about selection rule for vibrational spectroscopy. There are two selection rules. One which is known as gross selection rule, which tells that electric dipole moment of molecule must change when the atoms are displaced relative to one another. So, during the vibration electric dipole moment of molecule must change, then only it can show your vibrational spectroscopy. And the second is a specific selection rule which tells you that transition is only allowed when delta V is equal to plus minus 1. For homonuclear diatomic molecule, we discussed that vibration does not create change in your dipole moment, electrical dipole moment. So, homonuclear diatomic molecules cannot be studied through IR spectroscopy. Molecule without a permanent dipole moment can be studied if there is a variation of dipole moment with the displacement, and this variation can start from 0. For example, in CO2 molecule, certain vibrational modes are IR active because your permanent dipole moment can change on the displacement. The application of your vibrational spectroscopy in the calculation of dissociation energy. So, we have already looked at what will be the energy of different vibrational levels when we consider your anharmonic oscillator. So, for that your energy is given by V plus half SC omega E minus V plus half square XC SC omega E and plus higher energy terms. When we divide this energy term by SC, we will get energy of vibrational level in wave number unit, and that will be given by V plus half omega E minus V plus half square XC omega E plus higher wave number term. Now, one of the way to calculate WE and XC omega E is GV plus 1 is energy of V plus 1 level in wave number unit minus GV is energy of V level in wave number unit. When you subtract or when you take difference between these two values, these two terms, what you will get is wave number of transition between level V to V plus 1 and that can be obtained from vibrational spectroscopy. Experimentally you can obtain that, and when you plot that versus V plus 1, what do you expect? That it will give you a straight line with intercept omega E and slope minus 2 omega E x a. So, this is written here. Now, you see that if you plot this, versus V plus 1, your intercept will be omega e and slope will be minus 2 xc omega e. And that can be used to calculate your dE, which is dissociation energy, and the equation for this is given here. Now, we will discuss in the next slide how we can obtain this relation. So, there are two different kind of dissociation energy. One is the difference of energy of vibrational level where the energy is maximum and your 0, whereas the second is your D0, which is the energy difference between this and your V is equal to 0, energy corresponding to V is equal to 0. Now, to calculate V max and corresponding energy, what we will do is we will simply differentiate this energy term with respect to V, with respect to V. So, we expect that that will give you value of V max or value of V where energy is maximum, value of V where energy is maximum. When you do that, when you differentiate this equation 1 with V, what you are going to get is Sc omega e minus 2 V plus half Xc Sc omega e. Higher terms are neglected and that should be equal to 0 if we want to know the V level where energy is maximum. And when we do that, what we will get is V is equal to 1 by 2 Xc minus half, and this is the V max. Again, V max is the vibrational level whose energy is maximum, Okay, so EV max, or which is basically known as dE, is basically obtained by putting this V value in EV. Now, you see that V plus half is equal to 1 by 2 Xc. So, what you have to do is you just replace this V plus half by 1 by 2 Xc. When you do that, what you will get is dE or EV max, energy of the maximum, energy of vibrational level where your energy is maximum is your 1 by 2 Xc for V plus half Sc omega e minus 1 by 2 Xc square Xc Sc omega e. So, this is basically omega e by 2 Xc Sc minus, if you simplify this, what you are going to get is omega e by 4 Xc Hc, 4 Xc Hc, which corresponds to omega e by 4 Xc into Hc. So, this is the way to calculate dE, and dE is basically your maximum energy or energy of the vibrational level which corresponds to maximum energy, So, your dE is, if you remember that dE is equal to omega e square by 4 Xc omega e, and here you can simply multiply there at numerator by omega e and divide by omega e, then it will be omega e square by 4 Xc omega e, and that can be calculated by the previously shown plot. So, this is the way you can calculate dE in wave number unit. So, this is dE in your energy unit, and if you divide by Sc, then you will get dE in wave number unit. So, dE is given by omega e square by 4 Xc omega e Sc. This is in your energy unit, whereas if you divide by Sc, you will get dE in wave number unit, and so this is your dE in wave number unit, and if you subtract that by E naught, which is the energy of V is equal to 0 or 0 point energy, then what you will get is what is known as your d0. So, d0 is equal to simply dE minus E naught, and if you see here, so this is your energy of the vibrational level V, energy of vibrational level V where energy is maximum, and this is your dE, whereas dE minus this 0 point energy corresponding to V is equal to 0 will give you d0 value. So, till now we discussed vibrational spectroscopy of diatomic molecule. Now we will discuss vibrational spectroscopy of polyatomic molecules. So, if you go for polyatomic molecule, first thing you need to understand is what is the normal modes. So, if there is n atoms in a molecule, there will be 3 n possible movements, and so every atom moving in one of the 3 direction x, y, z. So, there is 3 n possible movements. Out of that, 3 are translational movements. So, all atoms in the molecule moving in x, y, z direction at the same time. So, you have a 3 translational movement. So, out of 3 n you have a 3 translational movement and 3 rotational movement, 3 rotational movements around x, y or z axis. So, out of 3 n now 3 is accounted for translational movement, 3 are accounted for rotational movement. So, left one is your 3 n minus 6 movements, and that is your normal modes of vibration in a molecule, in a polyatomic molecule. For linear molecule, they are bit exceptions, because 2 axes that perpendicular to molecular axis are identical, and that is why they have only 2 rotational degree of 2 rotational movements. And so, total normal modes of vibration for a linear molecule is 3 n minus 5. All vibrational movements of the sample can be described as linear combination of vibrational normal modes. Now, let us think about water. These are the 3 different normal modes of vibration. One is your symmetric stretching. So, everything is going in one direction. The vibration of symmetric H2O stretching is around 36-57 centimeter inverse. Then you have asymmetric H2O stretching, means one is going in this direction, then other will. The movement of other bond will not be symmetric, it will be just in opposite direction, and so you have a symmetric H2O stretching which have vibration around 1595 centimeter inverse, and the last one is your the bending vibration, and that happens around your 3756 centimeter inverse. Here in this you can see there are several different molecule and their vibrational wave number is given. For example, HCl symmetric stretching, so it has only one kind of stretching, so that is symmetrical stretching, and your wave number is 2991 centimeter inverse. Similarly, HF molecule, so for diatomic molecule you only have one normal mode of vibration, and for HF it is 4139 centimeter inverse. For H2O you have 3 different kind of vibration, we just discussed about that. One is symmetric, another is asymmetric stretching, and then your symmetric bending, and this value we have already seen. For ammonia there can be 4 different kind of vibration. Apart from symmetric stretching, asymmetric stretching, symmetrical bending, you have asymmetrical bending which happens around 1689.7 centimeter inverse. Similarly, you can go and calculate for other kind of molecules what will be the normal mode of vibration. The simple rule is for polyatomic molecule which is not linear, polyatomic molecule which is not linear, you have a non-linear molecule, basically you have 3n minus 6 movements or 3n minus 6 normal mode of vibration. For linear molecule you have 3n minus 5 modes of vibration. So, for example, for HCl you are going to have, HCl has 2 atoms, so 3n minus 5 comes out to be 1, and that is what we saw in the case of HF and HCl. So, diatomic molecules are going to have only one normal mode of vibration. For H2O, it is triatomic molecule and it is a nonlinear, so 3n minus 6, so 3 normal mode of vibration. For ammonia, you have your 4 atoms, so 3n minus 6, 4 into 3 minus 6. So, there are going to be 6 different kind of vibrations. Selection rules for polyatomic molecules is similar to what we discussed for diatomic molecules, but for polyatomic molecules some normal mode of vibration are IR active where others are not. A gross selection rule is applicable here also. So, displacements of a normal mode must cause a change in the dipole moment, only then you can see the IR spectra of that molecule, and then a specific selection rule is similar, delta V is plus minus 1. So, now we will go to Raman spectroscopy. So, Raman vibrational, and then we will discuss Raman rotational-vibrational spectroscopy. So, when light falls on a material, we know that how EMR, electromagnetic radiation, interacts with your sample. Light can be transmitted, light can undergo your luminescence, light can get absorbed, and scattering can happen. Scattering is also of two types, elastic scattering and inelastic scattering. So, Raman spectroscopy is basically complementary to IR spectroscopy. Radiation at a certain frequency is scattered by the molecule with shift in wavelength of the incident beam. It resembles IR absorption spectrum, but mechanism differs. In IR spectroscopy, your particle is moving from one vibrational level to another vibrational level. In the Raman spectroscopy, when you excite the molecule, it goes to some virtual state, and from the virtual state it comes back to one of the vibrational state. So, V double dash is equal to 1 by a scattering. So, you can see gap still remains same, gap still remains same. This is the difference between IR and Raman. We are looking at the vibrational modes only, but in IR change in dipole is important, whereas in Raman spectroscopy change in polarizability is important. We have already discussed Raman a bit in rotational Raman spectroscopy. So, I am not going to tell you in the detail, but we know that change in polarizability is important for Raman spectroscopy. Here excitation of molecules happen to excited vibrational state, whereas in Raman spectroscopy momentary distortion of electron distributed in the bond, and here asymmetric vibrations are active. Only asymmetric vibrations are active, particularly for triatomic linear molecule. Here your symmetric vibrations are also active. So, basic principle of Raman spectroscopy is light is scattered by the sample at various angle by momentary absorption to virtual state and then emission. So, absorption molecule does not go to a vibrational level, it goes to a virtual state, and that is what it is seen here. So, no change in electronic state. So, first it must be kept in mind that in Raman spectroscopy there is no change in electronic state. We are going from this ground state to a virtual state, and there are infinite number of virtual states, it can go anywhere. So, these are two virtual states you can see here. So, first during excitation it goes to this. Excitation can also take a molecule or a particle from a vibrational state 1 to this virtual state, and then so this is your ground electronic state, and there are these 4 vibrational states. So, from first vibrational state it can go to your some another virtual state, and if suppose on absorption it goes from 0 to this virtual state, it comes back to same ground state, then you say that it is a Rayleigh scattering. Emission energy is equal to your H nu excitation. In this case, in Raman scattering, what happens that it does not come back to same vibrational level. It is now coming back. If you compare between this one and or this one, it starts from excitation is from 0 vibrational state to this, suppose this is virtual V1 state, V1 and this is V2 state. So, excitation is from 0 vibrational state to V1 virtual state, and if you see, it is coming back from V1 virtual state to V is equal to 1 vibrational level, not to V is equal to 0. So, E is going to be less, and E is energy of emission is going to be H nu excitation minus delta E, and delta E is basically this difference between V is equal to 0 vibrational level and V is equal to 1 vibrational level. V is equal to 1 vibrational level. In anti-Stokes, so if you see here that there is excitation, the second excitation is from V is equal to 1 to virtual state V2, but when it is coming back, it is going from V2 to your V is equal to 0. So, here E is higher than H nu excitation, and that is higher by delta E amount, and this is called anti-Stokes lines. So, you have two different kind of lines, Stokes line and anti-Stokes line. Some scattered emission occur at the same energy, while other return to a different state. If it happens at the same energy, then you say that this is Rayleigh scattering, where H nu in is equal to H nu out. Whereas in Raman spectroscopy, there is a net change of energy, and H nu in can be either less than H nu out or can be greater than H nu out. In one case you say that is a Stokes line, and in the second one you say that is anti-Stokes line. So, resulting spectrum, you can see a Stokes line is this, where your E is less than E excitation, whereas in anti-Stokes line where E is greater than your. So, if you see frequency for anti-Stokes, frequency is going to be higher, and that is going to be nu excitation plus nu V, whereas for a Stokes line you have a smaller frequency, which is nu excitation minus nu of vibrational level V. Probability of emission is directly proportional to observed intensity, and Rayleigh scattering is quite greater than Stokes and then less than anti-Stokes. So, let us discuss about vibrational Raman spectra. Theory is almost same as rotational Raman spectra. So, when monochromatic radiations falls on a molecular sample in gas phase and is not absorbed by it, oscillating electric field of radiation induces electric dipole in the molecule, which is given by mu is equal to alpha into E, where alpha is your polarizability. Generally, the electric field, oscillating electric field is given by this equation, is equal to A sin 2 pi C nu bar into T, where C is velocity of light and nu bar is the wave number. V nu bar is the wave number. So, now let us think about how to express the polarizability. There is a difference between representation of polarizability in rotational spectrum in comparison to your vibrational spectrum. So, there is a difference between two different kind of motions. So, in the rotational spectrum, alpha is given by this equation, where alpha 0 r is polarizability when at the equilibrium position, plus alpha 1 r multiplied by sin 2 pi c multiplied by 2 into nu bar rotation and then multiplied by T. So, this term is significant. If you go for vibration, you will get alpha is equal to alpha 0 V, you can say 0 V alpha 1 V sin 2 pi c omega into T, where omega is again wave number, but this is wave number of vibration and this is wave number of rotation. One thing you will notice that in this case it is multiplied by 2, whereas in this case it is multiplied by 1. Now, question is why. So, let us think about a rotation of your O2 molecule, and what we have done is we have taken one 16O and this is 18 oxygen. So, this molecule when it is in this position, this is your the dipole moment, and when it comes to horizontal position, 18O goes this side. So, rotation is like this. So, 18O 16O, then your dipole moment will decrease. Now, again rotate by 90 degree, what you will get is 18O up and 16O down. So, again your dipole moment increases. Then on further rotation, this 18O will come here, 16O will come here. So, we are talking about this kind of rotation. Okay. So, 18O will come here, 16O will go here. In this condition also there is a decrease in induced dipole moment, and then this is the position on further 90 degree rotation. What you will get is 16O up and 18O down, and then you have higher dipole moment. So, now you see here that you started from this molecule and you are ending up with the same molecule, and this requires 360 degree rotation. Now, let us look at how dipole moment is changing during this 360 degree rotation. At this position it is up, then down, and it is up here. So, what does that mean is during one 360 degree rotation, it is going from first crest to third crest. So, first, second, third crest, and what does that mean is it is completing 2 cycles. So, during 360 degree rotation, 2 cycles gets completed, and that is why your wave number is written like 2 into nu bar rotation. Whereas during the vibration, now look at vibration, what is happening, 16O, 18O. So, this is one complete vibration. This is your equilibrium position, this is your extension, equilibrium position, compression, and then your equilibrium position, and then extension or stretching. So, you started with a stretching, you went to equilibrium position, you compressed it, you again went to equilibrium position, and finally your molecule is this bond is stretched. So, now you have gone from this position to this position. Now, you see if I plot this dipole induced by field during this one vibration, what I will get is here your dipole moment is higher, dipole moment is smaller, dipole moment is smaller, dipole moment is higher, and this is dipole moment is highest. So, you are seeing that you started from one crest and you went to the another crest. So, from stretched mode to stretched mode, you are completing one cycle, only one cycle, in contrast to the rotation, where 360 degree rotation corresponds to 2 cycles. So, here you do not write 2 omega, you write omega, where omega is wave number for vibration. So, if you multiply mu by E, what you are going to get is 3 different terms, and this I already explained you in the rotational Raman spectroscopy. When wave number is your nu plus omega, then you have anti-Stokes lines. When it is nu minus omega, then you have Stokes lines. So, these are the different terms. Alpha 0 V, I told you that corresponds to average polarizability during vibration. Alpha 1 V is amplitude of change of polarizability due to vibration. A is amplitude of oscillating electric field of incident radiation. Nu bar is wave number of incident radiation, and omega is vibrational wave number. So, in the case of vibrational Raman spectrum, you again get two lines anti-stocks along with your Rayleigh line, and the frequency wave number here corresponds to V plus omega and V minus omega, V minus omega. Now, we can discuss about selection rule for vibrational spectroscopy. Alpha is the polarizability, and alpha is also a function of x. Alpha can be given as alpha E plus d alpha by dxc x plus 1 by 2 factorial d2 alpha by dx at equilibrium into x square. So, this kind of calculation we have seen for vibrational spectroscopy. Same thing we are going to do it here. If we calculate vibrational Raman transition, the first terms when we put in this RV, first term is going to be 0 because your two vibrational levels V and V plus 1 wave function of two vibrational levels are orthogonal to each other. So, first term will tends to 0, second term will remain, whereas third term we can neglect for a small displacement. So, vibrational Raman transition moment can be given by this equation. RV is equal to your d alpha by dxc and this integral multiplied by this integral. So, your polarizability alpha, which is polarizability, must change with x if it is Raman active. And so, this is one selection rule, and the second one gives you delta V is equal to plus minus 1. So, first term is not 0 when polarizability changes with your displacement, whereas second term will not be equal to 0 when delta V is equal to plus minus 1. So, there are two selection rules. Delta V plus minus 1 is called a specific selection rule, whereas first one is known as gross selection rule. After this, now we know that Raman can be of two types, pure rotational Raman and pure vibrational Raman. We have already discussed pure rotational Raman, and in this lecture we discussed pure vibrational Raman spectroscopy. For rotational, there are three different rules. Delta J is equal to 0, plus minus 2 for linear molecule. For symmetric top, delta J is equal to 0, plus minus 2, and delta K is equal to 0. For asymmetric top, your delta J can be 0, plus minus 1 and plus minus 2, whereas delta K must be 0. So, this is the selection rule for rotational. For vibrational, then we have selection rule is delta V is equal to plus minus 1. We can also know intensity of Raman line, and we just calculated rotational Raman transition moment, and that is given by this equation. Intensity is proportional to RV square, and so by looking at how RV changes, we can tell about intensity of Raman lines. So, this is how alpha changes with x, and so depending on slope, you can say position and the slope at that position, you can calculate what will be the d alpha by dx square, and that is basically proportional to your intensity. In contrast to vibrational spectroscopy, what we can see is that this d alpha by dr is mostly positive, and it does not vary that much with r. What does that mean is that vibrational Raman intensity are less sensitive than infrared intensities to the environment of the molecule, such as solvent. So, please keep that thing in mind. A peak is more intense based on delta V is equal to plus minus 1. You also need to look at how polarizability changes with the distance, and that also determines your intensity of the peak. If you look at infrared Raman spectroscopy for diatomic molecule, you will have your three different kind of transition. So this is for diatomic. So you see S is equal to your, here you are going from, for example, take this case, we are going from V double dash is equal to 5 to V double dash, V dash is equal to 7. So again delta J is plus minus 2. We are going from your rotational level of one vibration to rotational level of another vibrational level. Okay, and so this is rotational-vibrational Raman, and this can be of three types, what is known as S, Q, and so this is your S type, and this is Q, and this is O. You see here in S you are going from 5 to 7, 5 to 7. So delta J plus 2, delta J is plus 2. Here you see you are going from 7 to 5. So this side you have delta J is minus 2, and in this case you are going from same place 7 to 7. So delta J is 0. So delta J is 0 corresponds to Q peak, whereas delta J is equal to plus 2 corresponds to S, and delta J is equal to minus 2 corresponds to your O peak. We know that energy of vibrational rotational levels, we have already discussed that, and that is basically GV plus Vj, and that is given by this equation. And now we can apply delta J is equal to plus minus 2 to know what should be the wave number for your S transition, O transition, and so you see this is, if I neglect anharmonicity and if I neglect your centrifugal distortion, then we have two different part, one corresponding to vibrational, another corresponding to your rotational level. And then you can calculate nu bar or wave number for S, O and Q transition, S, O and Q transition, and here you can see that this is not going to change because your delta V is plus minus 1 and when Raman rotational vibrational spectroscopy, but delta J is going to be plus 2. So this is for delta J is equal to plus 2, and for that the wave number is given by omega naught plus 4 Bj plus 6b, omega naught plus 4j plus 6b. And then you can also calculate wave number for O transition is delta J is equal to minus 2, and this is delta J is equal to 0. Delta J is equal to 0. So for O you will have this omega naught minus 4 Bj plus 2b, and for this you have omega naught. So you can see that, so this is your Q and this is O and this is S. So these are the three different kind of transition in rotational vibrational Raman spectroscopy. So intensity of normal Raman peak, just we discussed about intensity, how we can calculate. We have to look at how polarizability changes with X, that also tells you about intensity. Apart from that, intensity of the source, the concentration of active group will increase your intensity of the peaks. The power of Raman emission increases with the fourth power of the frequency of the source, and Raman intensity are usually directly proportional to the concentration of the active species. So there are two other things which decides about intensity. One is power of the source and the second is concentration of active species. So let us first understand what we mean by volume of ellipsoid and polarizability. It is important to understand polarizability because then you can understand how a molecule is Raman active, vibrational Raman active or not. Polarizability of molecule is generally represented at ellipsoid, and volume of ellipsoid is inversely proportional to a square root of alpha, where alpha is polarizability. So what does that mean is that if you look at this ellipsoid. So, in this direction your volume is less, whereas in this direction your volume is more. So, this is your minor axis and this is your major axis. So, what does that mean is, in this direction your polarizability is more, polarizability is more, your polarizability is high or more, whereas in this direction, vertical direction, your polarizability is less, since volume is proportional to 1 by root alpha, where alpha is polarizability. So, if volume is less, it means polarizability is high. And now you compare between these two, volume of ellipsoid, and you can tell that in this polarizability is high, polarizability is high, polarizability is high, polarizability is high. Now, let us think about, if suppose I am looking at CO2 and I want to know whether different vibrational mode of CO2 is Raman active or not, Raman active or not. CO2 has 3 fundamental vibrational mode. So, since CO2 has 3 atoms, so 3 n minus 6 is 3. So, it has 3 fundamental vibrational mode. One is symmetric stretching mode, and that is shown here, shown here. So, this is a molecule and you are basically stretching these 2 bonds. So, extension this side, this, so stretching is happening. So, when stretching happens you get this, when contraction happens you get this molecule. So, both bonds are getting stretched, here both bonds are getting compressed. So, if that happens, you say that the molecule has symmetrical stretching mode. The second kind of mode is bending mode, and here you can see that this is the normal molecule, and if you take both up, then you will get this one. If you take both down, then you will get this one. So, this is your bending mode, and the third one is symmetric stretching mode. In that one bond is getting stretched while other bond is getting compressed. So, in this case this bond elongated, this bond get compressed, while in this case this is compressed and this one is elongated. So, you have 3 fundamental vibrational modes of CO2. Ideally all are Raman active, because you can see that there is a change in polarizability, but in reality this asymmetric stretching and bending are Raman inactive. Now, let us first think about what is happening to polarizability. So, here you see you are stretching this bond. What does that mean is that the electron cloud is more polarizable, since there is a greater distance between nuclei and electron cloud. So, you will see that volume of ellipsoid is, volume of polarizability ellipsoid is smaller, whereas in the contraction case polarizability is more. What does that mean? Volume of ellipsoid is going to be large, Similar is the case with this bending mode. In bending mode you can see that here your cloud is elongated. What does that mean is polarizability along the major axis is smaller, whereas in this case polarizability along this direction is higher compared to this CO2. Same thing here, polarizability along this axis is higher compared to your normal molecule or molecule in equilibrium position. Now, the third case, asymmetric stretching mode. So, you can see here that in this case your polarizability is higher in the equilibrium, where In this one, polarizability is going to be smaller. So, polarizability is greater in the CO2 in equilibrium mode. Polarizability is smaller along this axis, if you do asymmetric stretching, and same case is here. So, it looks like that polarizability is changing, but in reality we will see that in the last two cases polarizability does not change. So, for that what we need to do is we need to look at change in polarizability with displacement coordinates. So, to understand why the other two modes are Raman inactive, what we need to see is we need to look at change in polarizability with displacement coordinates. So, what I mean by displacement coordinates, that for a stretching motion it is a measure of extension and compression of the bond under consideration, whereas for bending motion it is the measure of displacement of bond angle from its equilibrium value. So, what I mean is that plus and minus value of E refers to opposite displacement direction. Once we know that, let us see the plot. So, this is plot for symmetrical stretching mode, and you can see that your epsilon is plotted against alpha, and now you see this is your equilibrium position. So, you are at this point, and now what you are looking at, what happens when you compress the bonds or stretch the bonds. So, this is your stretching, and you can see that stretching, what happens, you are going towards plus E, and plus E, here your volume ellipsoid is smaller and polarizability is higher. So, you can see this polarizability is increasing. When you do compression, what you mean is you are looking at this side, negative side of extension, and you can see that your volume of ellipsoid is larger, it means polarizability is smaller, and so polarizability is dropping with the compression. So, if you look at this point, what you will see is near equilibrium position, if you look at a small displacement, it has a slope. So, you can see that there is a slope. What does that mean is, for a small displacement, motion changes polarizability, and thus the symmetrical stretching mode is Raman active. Now, let us think about bending mode. So, I already discussed that this is your equilibrium position and your polarizability is going to be smaller and volume of ellipsoid is larger. So, now you are looking at plus E minus E. So, when you do suppose displacement in this direction, which is basically here, what you see is volume of ellipsoid decreasing, it means polarizability is increasing. So, polarizability is increasing. Now, if you look at this case, where what we are doing is we are bending both CO towards downward, and in that case again volume of ellipsoid is decreasing, and that means polarizability is increasing. So, you basically get this kind of curve when you plot alpha versus G. Now, if you go at equilibrium position and try to draw a slope for a small displacement, what you will see that your slope is 0. What does that mean is d alpha by d E is equal to 0. So, basically for a small displacement there is no effective change in polarizability, and therefore, bending mode is Raman inactive. Now, let us think about the third case, asymmetric stretching mode. In this again your equilibrium position, you have a smaller ellipsoid. What does that mean? That alpha value is higher, and if you do asymmetric stretching. What does that mean? Extension of this bond and compression of this bond, then we will get a greater ellipsoid volume. It means polarizability is decreasing. In this case also polarizability is decreasing. So, you get something like this curve when you plot alpha versus g. And now again you can go at equilibrium position and look at the slope. Here again slope is 0. What does that mean is, for a small displacement d alpha by dE is equal to 0. And what does that mean is, for a small displacement there is no effective change in polarizability, and what does that mean is that this mode is also Raman inactive. So, basically you have to look at the change in polarizability around equilibrium, and you must have to think about a small displacement, and if slope is 0, it means that particular mode is not Raman active. If slope is positive or negative, it means polarizability is changing, and when polarizability is changing means it is Raman active. So, for CO2 molecule we have looked at 3 different vibration mode: symmetrical stretching, bending and asymmetrical stretching. The first one is Raman active, but it is infrared inactive, whereas bending and asymmetric stretching are inactive modes in the Raman spectroscopy, whereas they are infrared active. So, conclusion is, no vibration is simultaneously active in both Raman and infrared, and that leads to well known rule of mutual exclusion, which says that if a molecule has a center of symmetry, then Raman active vibrations are infrared inactive and vice versa. If there is no symmetry, then some vibration may be both Raman and infrared active. Converse is also true, that is, both Raman and infrared are inactive, then molecule has a center of symmetry. So, this rule of mutual exclusion is for molecule with a center of symmetry, and when the molecule has center of symmetry, then either the mode is your infrared active or Raman active. It cannot be both Raman and infrared active molecule. So, this is all about theory part of your IR spectroscopy. Now, what we will do is we will look at the application, and IR spectroscopy has wide range of application. Most important one is your identification of substance. So, most of the organic molecule can be identified, or particularly their functional group can be identified through IR spectroscopy. For that you need to just compare a spectrum of your sample and a reference sample. Two samples are not going to have identical IR spectrum. So, you take 2 molecules and you try to see their IR spectrum, that is not going to be same. You must certainly, we are talking about when those 2 molecules are in identical conditions. One disadvantage is that we cannot distinguish enantiomer. Fingerprint region 1500 to 400 centimeter is very important, because even a small difference in structure and constitution molecule will show significant change in the peaks in the region. And so, it is very important tool, IR is a very important tool to identify an unknown compounds. I will give some examples to you. So, look at this molecule. So, here you have CH3 C double bond CH, CH2 CH3, and this is a cis trans, cis 2 pentene and or trans 2 pentene, and you can see that there are a lot of differences in IR spectrum. Particularly you see this cis you have here, and for trans it is here. And similarly you can look at the stretching, sp2 CH stretching, sp3 CH stretching. So, just by looking at a spectrum of 2 pentene samples, you can tell that which 2-pentene has cis configuration and which one has trans configuration. Now, look at this your 2,3-hexane, and this is your 2-pentane and 2,3-hexanes. Just a small change, one methyl group you have attached to this part, and you see fingerprint region, it is totally different. Fingerprint region is totally different. And so, just by looking at fingerprint region, you can tell about which molecule is present in the sample. No two molecules has identical IR spectrum. So, just by comparing with the already available data in the literature, you can know what molecule is there in the sample. This is very simple method, IR is very simple method to distinguish between two polymers. For example, polyacrylonitrile and polyethylene terephthalate, just visually you cannot distinguish it, but just looking at IR you can distinguish between these two polymers, because these two polymers have different functional group. In first one you can see in polyacrylonitrile there is nitrile group, and nitrile group absorbs at 2250 centimeter inverse and get a band around 2250 centimeter inverse in IR spectrum if you have polyacrylonitrile sample. This polystyrene you have ester group. So, just by looking at frequency absorption of ester group, which is around 1735 centimeter inverse, you can know that whether you have polyethylene terephthalate or polyacrylonitrile. So, two polymers can be distinguished using IR spectroscopy. I will give few more examples. For example, natural rubber and butyl rubber. We can differentiate between these two different kind of rubbers, because natural rubber is your polymer of isoprene which has a double bond, whereas butyl rubber is your polymer of isobutylene, and you see here there is no double bond, and in natural rubber you can see a band around 1630 centimeter inverse, which will not be present in a butyl rubber. Similarly, we can distinguish between polyethylene and polystyrene. As you can see that polyethylene is your polymer of ethylene molecule, whereas polystyrene polymer of a styrene molecule, and a styrene has a aromatic benzene ring, and for aromatic benzene ring CH comes above 3000 centimeter inverse, whereas for aliphatic CH bond your band comes below 3000 centimeter inverse. So, just by looking at simple IR spectrum of these two polymers, we can distinguish these two different polymers. We can also distinguish between cellophane and polypropylene. Again, cellophane is a polymer of cellulose acetate, whereas polypropylene is polymer of 1-propylene. So, now you can look at in cellophane you have acetate group which shows an absorption band around 1710 centimeter inverse, whereas for polyethylene this single band comes around 2900 centimeter inverse. So, just by looking at simple IR spectrum you can distinguish between these two polymers. So, this is about finding out whether molecule or identify the molecule in the sample. The second thing is we can even get structure of the compound using IR, and for that we need to combine this with other spectroscopic technique like NMR, UV visible. Particularly functional group can be very easily identified by use of IR spectroscopy. For example, CO carbonyl band absorbs around 1717 centimeter inverse, whereas you can find a bond around 3400 centimeter inverse if molecule has OH group. And absence of band of that particular group indicates absence of that functional group in the compound. So, for functional group prediction, IR is one of the most suitable and easiest method. One example I have already given, that you can distinguish between two different isomers. Here again there is one case where you have cis and trans isomer of 3-hexene, and that can be distinguished by looking at the fingerprint region. In cis 3-hexene, you will get out of plane CH deformation band near 970 centimeter inverse, whereas in trans 3-hexene you will get CH deformation band near 700 centimeter inverse. So, cis and trans can be distinguished by use of IR spectroscopy. The third application is monitoring the progress of reaction. A reaction progress can be simply monitored by using IR spectroscopy, and it is quite simple. You can either look at disappearance of characteristic absorption band of reactants, or you can look at rate of increasing absorption band of a particular product. So, for example, if we are looking at this transformation from alcohol to keto group, so reactant has OH functional group. So, you can look at rate of disappearance of alcohol and then you can study the kinetics, whereas you can also look at increase in absorption bond of CO to look at the monitoring of progress of reaction. So, suppose band around 3600 to 35 centimeter inverse disappears, then you know that your reaction is complete. Similarly, there is second example where we can look at the progress of reaction. So, this is simply hydrolysis in presence of aqueous NOH. So, you can see that there is NH2 group and there is a CN bond. So, there is a CN bond. So, this CN bond absorbs around 1100 centimeter inverse, and this is in the reactant, and now that is missing in your product. In product you have keto group converting to your this COO minus group. So, what you will see with the progress of reaction, that absorption band due to CN bond will disappear, whereas your SARC band as 1670 centimeter inverse, which is because of CO bond in amide will shift to higher side, because now you are going from CO bond in amide to CO bond in ester. CO bond in ester, and CO bond in ester basically absorbs at higher wave number. Apart from these three, we can also detect the impurities contaminants, and this is very important for particularly for quality of sample, looking at quality of the sample. Generally what we do is we compare sample spectrum with a spectrum of pure reference compound, and by that we can know whether there is impurity or not. People try to look at ketone impurity in alcohols. So, most of the alcohols has ketone impurity, and just by looking at the absorption band of C double bond O, we can know whether that impurity exists or not, and we can also do quantitative analysis. Generally, detection is favored when impurity possesses a strong band in IR region, whereas main substance don't possess a band. Then only we can. So, for example, when we are comparing between ketone and alcohol, ketone has a band due to CO, whereas alcohol has a band due to OH, which is absent in each other. Okay, so there is one example where contaminant extracted from a filter of air conditioner was looked at, and it was tried to find out whether that contaminant is due to mineral oil or cooking oil. So, generally mineral oil consists of higher alkanes, whereas cooking oil has various saturated, unsaturated, polyunsaturated, monounsaturated fats. So, if you know this difference of structure, then you know that cooking oil must have your absorption band due to unsaturation, and if your contaminant is from cooking oil, you will see a strong absorption band at 1735 centimeter inverse, and that is because of unsaturation. Thus, contaminant, if we see that there is a band around 1735 centimeter inverse, then contaminant must be, contaminant could be cooking oil. So, the next application of IR spectroscopy is determination of the bond strength. So, IR stretching frequency, you know that it is given by 1 by 2 pi root k by mu, where k is spin constant and mu is reduced mass of the atom. So, now again mu is related to R, your mu is related to R, whereas k is related to bond strength. So, just by looking at k, you can know that whether, or by looking at k you can determine the bond strength. So, if bond strength is high, then k is going to be high. So, by knowing the stretching frequency from the experiment, we can calculate the stiffness of a particular bond. There are other applications. For example, if you are trying to look at blood glucose level, and we generally know whenever we go to hospital, they take your blood and then look at your, then do some testing to know the blood glucose level. Okay. So, for that you require a new test strip, and that increases the cost of such a device. This is a non-invasive technique, and here your wavelength of 1550 nanometer is chosen due to high signal to noise ratio for glucose signal. So, in this IR transmission, your instrument is basically used across the ear lobe to measure glucose. So, you do not need a blood sample, and basically what is done is that a light source and a light detector is placed on either side of ear lobe, and then amount of near IR light passing through the ear lobe depend on the amount of blood glucose in that region. So, ear lobe was chosen due to absence of bone tissue and also because of its relatively small thickness. So, in this case you can see that without taking the blood sample, we can know what is the glucose level in the blood. So, there are a lot of other applications of IR spectroscopy, and in the next lecture we will discuss some of them. And but one thing is clear, that for a chemical molecule, IR spectroscopy, for analysis of chemical molecule, IR spectroscopy is must, and it is your non-invasive technique, and then it can very easily tell you about the functional group of the molecule. Thank you.